এইটো ইয়াত নাহে নেকি এইটো অকমান দেৰিকে দেখি নেকি চাগে তাতে So আপনি start করি মানে this is started already they can see right okay. So I can start now okay so yeah I think hello everyone so when is your exam exactly it is there for tomorrow or who I mean I'm hoping that 2-3 are watching and some of you have exam on probably you are registering for exam enrolling for exam you may not I mean all of you may not be interested for exam but whoever are interested for exam when is your exam okay yeah I have some of your queries so tomorrow probably tonight I will upload it I was out of campus for some time so somehow I could not upload those queries but anyway so I will upload it probably if you have day after tomorrow you have exam so I will upload the query so yeah what will happen in SHPP about after L by C time L by C time I think yeah I saw one of your queries I think you only asked probably right so I don't have this attachment I think here with me so I think you have because I have only on a hard copy of these questions so what you are probably saying is L is the length of the projectile bar right so I think answer to your question is I think what you are asking is first the compression part of the wave will advance and then the rarefaction will advance I think that's what you are asking I mean what I understood is after L by C the first L will be your compression and then second part will be rarefaction the entire thing will define the wavelength that's what I remember what I mean you have attached something I think that's what the answer is for your you have several questions in that I think that is the answer to the first question and I actually did not understand one of those questions probably second or so second question is just one second I wrote somewhere your yeah this I think second or so question I actually did not understand exactly but if you have high velocity of the projectile I think that can be different because shock wave can be generated and that can be have really high it can have high amplitude so that can change the situation I mean somewhere you probably asked about that but I think L by C is that's what I mean if I remember correctly so first the compression part will move and then after that the rarefaction will move and that entire thing will add up to wavelength so some of the other queries I have the just printed out the queries here so what is the nature of shock waves produced in impact of two flat surfaces mostly if it is a flat surface I think it will be normal it's normal wave and elastic plastic I think basically the we discussed the shock wave with the plastic wave but I think it depends on the material if let's say your material is some soft polymeric material let's say which is kind of very elastic and there is no plastic deformation happening I think recently I attended a conference I saw some Sweet Hopkinson preserver experiment on soft gel it's a gel soft material and that's a very well-known professor from US, an Indian professor. So he told that there is no plastic wave in there. I mean, he explained it like that. So I think he is doing some shear Speed Hopkinson experiment, not the usual compression experiment. And then he was showing, and then someone asked him that okay, whether it will have a plastic wave. I mean, he's saying that no, there may not be a plastic wave here. All everything is elastic. I mean, just I remember this thing, and that's why I mentioned. So it surely depends on the material. So basically, when we discuss about metallic material, I think yes, that is plastic. Plastic deformation will happen, and that's shock wave is, I think, we can call the nature is plastic. And another question is, yes, I mean, there should be a minimum velocity, right, that we understand. If you, let's say, any material, if you hit with a hammer with a very slow speed, it will not surely generate shock wave. It will not generate, shock wave, right? So if you have a minimum impact velocity, that means, you should hit it very hard. Let's say you are like bullet impact or projectile impact. So that kind of impact can give us shock wave. So otherwise, that will not be shock wave. And then, yeah, there is a question on pressure P1 and P2 should be the same after impact, otherwise second pulse will form. So that is, I think, how do we know that the second pulse has not been formed after the impact? So is it always mandatory that P1 equal to P2, or this is just an assumption? Oh, I think this is from, if I remember correctly, this is from the impact, planar impact of the shockwave chapter, right? So that the planar impact, yes, that is, I think, correct. This P1 equal to P2 is an assumption, and it's an ideal case, like where I think we want to avoid the formation of a second pulse. Yeah, that is, I think, correct. Yeah. So and then there's another question: in the planar and normal impact, what will happen if the impact is not planar? If all the points do not come in contact simultaneously, and during the process, why we are not considering rise in temperature? So I think non-planar impact will it should produce both compressive and shear wave if it is non-planar. So you are let's say planar means you have the target, and you have the your projectile or striker here, and you have the planar impact. Or if it is non-planar, I think, and then it should produce both compressive and shear waves. And I think the interaction of the waves, which we did not discuss much because these things are a little out of syllabus. So interaction of the waves will be complex. I mean, interaction is actually really, I think, a little complex to understand. There are a lot of interactions can go, the boundary reflection from the boundary and other things. But here, the interaction between, you have the compression wave and the shear wave, that can be also something to understand, and may not be very straightforward. And then I think you are asking about that analysis. I'm not very sure. So you are asking about that analysis where the rise in temperature is considered or not. What I remember is that is just to determine the pressure from, I think, momentum balance, conservation of momentum. So I think that will not consider the temperature. That's what I feel. So that is what I think. Yeah. So I will. How much time will be required for the motion of the projectile to transfer into the motion of the projectile to transfer into the incident bar? What is your question exactly? So anyways, that time is like, as you can understand, that twice L by C is the time of that's what you were asking, that twice L by C, I think. And then okay, I'll read another question also. The gaseous pressure is 1 atm, 1 atmospheric pressure. So the change in pressure for shock wave is of the order of atm or not? That's what you were asking. And what is the analogous of pressure in solids? I think we use the word, I mean, the term pressure in solids as well. I mean, right? So that's what we did in the plenary impact and all. We have used pressure. But gaseous pressure, I think that is shock wave, right? So shock wave actually have a very high pressure, I think. It's not generally, we don't discuss about pressures of 1 atm, that is atmospheric, I mean, pressure. I think that is, we don't talk generally order of that, right? This pressure can go up to like gigapascal. That's a very high pressure generally, during the shock wave. And okay, are you trying to say that with a decrease in atmospheric pressure, the sound speed will decrease? Or can I say higher the density of medium, higher the sound speed? So I forgot exactly the what part of the video, but first thing is with higher density, as we know, just when we have the simple sound wave elastic wave equation, that is your square root of E by, I think, C, right? That is Young's modulus and yeah, rho actually, sorry, density. So I think it is the opposite, whatever written. So I think the density, if higher the density, I think the wave speed will be lower, but it depends on the Young's modulus also. For example, you have iron and aluminum, so whatever you mentioned here. So iron has a, as you know, higher Young's modulus. It's quite higher than the Young's modulus of aluminum. Uh, so it's like, let's say, 200 gigapascal for iron and then 70 gigapascal for aluminum. But other thing is that I think um, your density is one third for aluminum than, as compared to iron, right? The iron has a 7,800 and aluminum is at 2,700, 2,700 kg per meter cube. So if you have this relation square root of E by rho, then I think, though, I mean, although Young's modulus and density both are high for iron, and because your density is one third for aluminum, but Young's modulus is maybe not one third, but a little less than half. So that ultimately will be, it looks like that, I mean, if you can imagine, right, the square root of E by rho, then if you can find out that wave speed of aluminum should be more than iron. That is the case. If you see the, I think, see, there will be a table, I think, in the elastic wave chapter of Mark Mayer's book. I think there you can check that. So what I understand is it should be like, let's say, if I remember correctly, it is like, let's say, 6 kilometer for aluminum and will be a little less in iron. Let's say 5 point something kilometer per second for wave speed. But then decrease in atmospheric pressure, the sound wave will decrease. Um, it is, I think, there is a relation, if you remember, that is with pressure and density, that you can get it, I think, from probably where you have got this video. So basically, higher gas pressure may result in higher sound speed. So but significant change of sound speed can be experienced only at very high pressure, not like little higher than, let's say, atmospheric pressure. But if it is really high pressure, that increase in pressure, gas pressure, will uh, increase that sound speed. But you can check the relation, because you may be confused with density and again pressure. But it is partial of, I think, pressure with respect to density. So that may be a little confusing for you. But at very high pressure, sound speed is expected to increase with pressure. And then sound velocity will be more in a medium with a higher density than lower density. Yeah, I think this is yes. I think this is also yes. The same explanation probably earlier. That is, Young's modulus is equal. If it is equal for both, then sound velocity should be, lower with, I mean, higher density material. Okay, you wrote something motion of last one, the rear end of the projectile. The time twice L by C is compression part only or compression and tension? Uh, I think yes. You are saying that rarefaction, right? I think it is for both the compression part and rarefaction. The entire thing will make that the wavelength. I think if I am getting you correctly, so that will, I think, both the, I think, compression and rarefaction part projectile hit the wave will be reflected back, and uh, as soon as the projectile hit the wave will be reflected back, and so the compression part will be in the bar for twice L. No, but I think if you have drawn something in that, right? So I think that's what you were asking, I think, or otherwise I will get back to you what you have written. But this is a little bit difficult for me to understand. I mean, yeah. So we were calculating the stress induced by applied on curved surfaces, force per projected area. Uh, can you tell me where exactly from you are saying? Sorry, I actually most of the things I may forget because this course. I mean, not in touch with this course because last year only I recorded these videos, and here we don't teach that course. Can you please tell me where exactly you are saying about calculating the stress induced by force applied on curved surfaces? From where actually you got it? No, but just I want to know, like, from where you are asking me. So I just need to know because um, yeah, I just need to know from where you are asking because I need to check what exactly that. So um, yeah, we generally, I don't know where we have that kind of approximation. So but generally we take the direct area, right? I am not so sure. Sorry. So you can please write it explicitly where I need to check actually. So then I have another query. Let's say wave velocity amplitude of plastic wave is higher than okay, somewhere I wrote high amplitude isentropic disturbances. Actually, this is only for shock wave. High amplitude isentropic disturbance travels faster. I think I wrote something not very, I mean, easy to understand, but that is mostly it is a shock wave. If it is higher amplitude, it travels faster. I think somewhere earlier also we wrote this answer. Probably you can check whatever probably we posted the answers there, it will be there. So generally what happens is the maximum displacement of the atoms from the equilibrium position, right, is the amplitude, that is we call the amplitude. And for plastic and shock wave, the higher amplitude wave will result as higher velocity. That's what we discussed, right? Like elastic wave will go fast, but that is not kind of, this is just a because amplitude is low only just as we discussed in the dynamic first deformation. We have drawn some atoms, and this is just to and fro motion, but it will not be so disturbed that the bones will break and you will have permanent some deformation. So that's why the elastic wave travels faster. But when it will be too much disturbed, the high amplitude, so then I think the plastic deformation happens. Let's say kind of material similar to metals or this kind of materials, and then what is says is high amplitude disturbances travel faster. That means higher amplitude, actually higher amplitude wave travel faster. So then our one part is elastic wave, that is totally different, and the plastic kind of waves are, let's say, is also very different. But within the plastic kind of wave, not kind of plastic wave, let's say we keep shock wave also inside that. Then within the plastic wave, higher the amplitude, the higher will be the velocity. So that's what, because that it can transfer the disturbances faster. Okay, you have mailed you the attachment. No, I have the attachment, but I cannot see right now. No, I have the attachment. I have not, but I don't have right now with me because I got a hard copy here. So I understand you have drawn something, and I think you have 3 4 questions in there. So I will check it, and I need to check. But what you probably wrote is, what I understood is correctly, is twice L by C should be the both the things. I think that's what you asked. And but yes, I think second or third question I mean could not get exactly like what you were asking. And yeah, then as an okay, shock wave is defined as the discontinuity of pressure, temperature, and density with the variation of only if the variation of only one parameter happen and the other two don't appreciably, we call it a shock wave. So shock wave generally is known to be generated due to high pressure. So whatever we are discussing, those shock waves are generated due to high pressure. It's very high pressure, and the generated shock wave produces the discontinuity in the shock front. That's how we discuss now, right? So yeah, basically it is a high pressure event, and whatever shock wave will generate, that will have a discontinuity in the pressure and density. And yeah, that's how we can say, like, but it is we don't discuss, it is very unlikely that you have temperature is high and then shock wave will generate. I think that way it will not work. Only we discuss the high pressure, the high pressure will generate shock waves, and that generated shock wave front will have discontinuity in pressure, temperature, and density. And don't very appreciate, yeah, that's then uh, the wave speed remains the same and local speed uh, yeah, that is actually, the wave speed remains the same and local sound speed varies with variation of local pressure. Why does not happen every mechanical wave? It is again, I think this is because happens at a very high pressure. At very high pressure, you can think that way. So it's not kind of a normal pressure phenomenon. So then I think it can vary with otherwise, in simply if you have, let's say, sound wave also, and little increase in pressure uh, will not affect the waves, but I think temperature can have more effect in even in kind of sound waves. If you have lower temperature, probably it can have more influence. So yeah, oh, what will be pattern for example? Okay, That is, in anyways, it is known. I will come to that maybe in the last. So, okay, I'll go to that. And cylindrical rod is, let's say, cylindrical rod is supported, and stress on the supported portion is. While designing core which is supported simply supported beam, and they assume that there are a compressive stress on the compressive stress on supported portion. But I don't know what is you are asking, but still I think I believe this is, I mean, sorry, but I actually I'm getting a little difficulty because it is not probably not related to our course. I mean, it's not probably what we discussed, right? About this cylindrical rod. I actually didn't understand exactly. So maybe, but anyways, this will not come in exam. So I think we can discuss more. But this is I didn't get exactly from where you got from the course, but it may be a different your strength from materials or some course, right? Maybe you can please explicitly write like which chapter, then I can see and let you know where probably I thought maybe I have made some mistakes maybe. And so then I'll then what are other maybe other questions? Some other questions are I think that impedance matching technique, basically that's a good question, but the how the we actually, yes, we have, I think, the pressure and pressure plot, right? Pressure and UP, I think whatever you told, that graphical solution is called an impedance matching technique. We are equating the pressure, I think, right? And y-axis is pressure and x-axis is, I think, that is what that is particle velocity, I think. So that probably what I remember, this is the pressure, because we, I think, wrote it like pressure, pressure of target and pressure of projectile, I think, right? The kind of UPT or UPP. No, not UP, sorry, PT and PP. So these pressures of the pressures, we, I think, made it equal, and then that way we solve the problem in that graphical solution. But those pressure depends on the impedance or resistance of the material. So that's why it is, I think, called impedance matching technique. So and also equation of state is, does the equation of state is only valid for metals? Okay, that's a good question. I think I did not mention. Can it be applied to composite like concrete, an isotropic material? What order of equation would be used for it? Yeah, I think we did not discuss about this, right? I mean, this is whatever in the course is mostly for metals. So, uh, yeah, so the most commonly used EOS, generally EOS, I mean, that means equation of state. Um, the most commonly used EOS is the relation between shock wave velocity and particle velocity, right? Um, it can be otherwise also. I mean, because we have different shock wave parameters, we have other shock wave parameters as well. So some somehow I feel that you can use other relations as well. But this is the most commonly used, accepted equation. So this is, you can see that this is a linear relation, right? US equal to, let's say, C, I think, S multiplied by UP. So these kind of relations are mostly taken for metals or alloys, let's say. But this, I think, people use it for even for polymer or even for composite as well. That is, they can take some assumptions and they can use it. I have seen it, probably you have also seen somewhere if you have just did some literature review on this. But if it is really an isotropic, like if you have concrete, yeah, concrete, I'm not very familiar because because I am not from, my background is like we do not study much on concrete, but composite material, let's say it's an anisotropic material. The relation will be non-linear. So basically, first here you have a complete linear relation with US and UP, shock wave velocity and particle velocity. So it will be non-linear means you will have extra terms. Generally, I think what I can see, from literature, like you have extra term, more than two terms, which will have non-linear part in it. I mean that the relation will be non-linear because of the extra terms. So for concrete also, I think you will get equations if you are interested in concrete, or if you are doing research on concrete. So I think better you please directly search equation of state for concrete. I have seen earlier that concrete, they work on concrete, and their equation, I'm not very sure, but it should be surely it will have a non-linear part, or sometimes maybe some people may even have some assumptions and they can still use some linear very simple equation. I think it is very easily can be found, so you just search if you have not done it. So equation of state for concrete, you will get it. And I have probably I can give you some composite papers, probably I have saved somewhere, and equation of state for composite, but that is also not very difficult to find. You can just search equation of state for composite, you will get it. But as I told, this will not be linear, although some people may use linear relationship, and with some other some approximation they can use. Actually they probably might have used it in some studies. And so yes, so I think what are other questions? Maybe there are a lot of questions here, and these I need to check. The one question is this thing I need to check. What are the factors? Okay, if a pulse is transmitted into a material that has an amplitude exceeding the elastic limit, this pulse will decompose into an elastic and plastic wave. Why will pulse or wave will decompose into elastic and plastic wave? um, I think, yeah. So simply speaking, I think elastic pulse, when the elastic pulse will travels, and what we see, the permanent deformation happens, right, in metal. Like if you are talking about the material with, if you have a very small amplitude, elastic wave, that is fine. Otherwise, if the amplitude exceeds the elastic limit law, what will happen is the elastic wave will go, because as you can understand that the elastic wave doesn't need to disturb the material much. So it's like small back and forth motion. And as you know that atoms are already vibrating, that we have discussed in the initial chapters, right, initial introduction chapters. So these will back and forth motion of the is already there, because atoms are vibrating, and so you are giving some extra push, and that's why these atoms will let's say move little more than the usual vibration distance. So then this elastic wave will move, and then if it is has a higher amplitude, so with that elastic wave there will be something which can actually like can permanently deform the material. So the permanent deformation of the material will cannot go with that speed. So the permanent deformation will happen, and then that disturbance front, that means I'm talking about the plastic wave front, so that certainly cannot go with that speed, elastic wave speed, right? So that's why it will have I think hopefully this is the answer to your questions, right? So that is decomposed into elastic and plastic wave. So first it will, that disturbance which doesn't disturb the inherent structure of those, let's say, bonds, atomic bonds, so it will not break the atomic bonds. That wave will proceed. But the other guy who wants to disturb by breaking of bonds, he will actually kind of take more time to breaking the bonds. Let's say I'm just explaining in that way, but as you know, in plastic deformation a lot of things are involved. I mean, it's a little complex, and you have dislocations and other things. But just to imagine that this other guy will take more time, and because he is fighting with this, to breaking the bonds, so that's why it will follow the other guy, but it will have less velocity. And yeah, that's what. But then this pulse will decompose. Why will the pulse will decompose? Yeah, that's what the question, right? I think, yeah, that's hopefully I answered the question. And the other question is, there is follow-up question. I think the plastic wave velocity is less than elastic wave velocity, so the wave disperses itself. How does the dispersion of wave affects the strain of the wire? This is probably from von Karman experiment, I think. Right? This is how the plastic wave velocity is less than elastic wave velocity. So, see, these wave dispersion is kind of, I think you are talking about. Yeah, dispersion is a little bit, I think, different in different sense. But here, I think what you means is. Uh, I mean, you are saying that the elastic wave goes ahead, and the plastic will be behind it, and then there'll be nobody to fight with this wave, and to disperse, I think. So generally, this kind of mechanical wave dispersion means, uh, I think, interaction of other waves with that wave, and then that will make this wave disperse, or it is let's say is reducing the intensity of wave, let's say. So what happens is, if you are saying about a wire, and okay, you are saying that the elastic wave is going ahead and the plastic wave is now free. I mean, there is no wave to disturb it, but it is not correct, because your boundary will be there, no? So this, because the small diameter, it's a diameter wire, so there will be reflection from the boundary. These waves, I think that boundary reflection will interact with the plastic wave. Also, it may be like that the elastic wave will go and hit the boundary on the top and come back, reflect, and again it will maybe hit the plastic wave, because your wire is like a vertical. I think the elastic wave will go and to the top, and then it may even come back. Let's say you have a rigid support and it can come back, and I think hit the plastic wave which is going behind it. Or otherwise, even the plastic, there will be some reflection of these waves from the boundary. I think that boundary reflection can also disperse the wave. I think that's the answer to your, I think, question. And yeah, there are again some other questions on dispersion. That's what I think. Uh, Both the waves never stated together. Plastic wave is following the elastic of dispersion phenomena takes place when two or more waves with different wave velocities start to move together. Uh, yeah, that's what I think. The answer is kind of same. That reflection from the boundary, or sometimes, let's say, if elastic wave reflects back from the other end, then these interaction will happen. And but you are writing this kind of this monochromatic wave. I think this dispersion is not exactly what we discuss in light wave, I think. But dispersion, I think, in the light wave is a little different. I think, but that electromagnetic wave, you have, sometimes we call it, I think, from white light to different colors light. That is dispersion. But I think in mechanical kind wave, in this kind of stress wave, we generally we indicate dispersion as a that interaction of the wave with let's say boundary waves, or boundary means reflected from the boundaries. Yeah. So what I meant in the even in the earlier question, that reflection from the boundary means you have a wire which is a low diameter, I mean very less diameter. So then the boundary means that cylindrical, the outer surface. So that it can have some reflection from there, or otherwise it can even, the elastic wave can go and hit at the top and come back and then hit the plastic wave. That's what happened in other experiments, if you have seen that. And so this, okay, the Taylor experiment. Okay, I think yes, Taylor experiment. This is material assumed to be, I think, say elastic, perfectly plastic. How will the behavior of the material will change? Yeah, the behavior of the material, it changes means generally, um, I think, uh, if it is perfectly plastic, basically we are not taking the velocity, plastic wave velocity as zero, but certainly if you increase the strain hardening, that means you, let's say you have, imagine the stress strain curve, your slope of the curve is now increasing, the plastic part of the slope of the curve is increasing, then um, I mean, if you remember from the that plastic wave velocity formula, like which is not square root of E by rho, that is the slope of the curve instead of E, Young's modulus, which is for elastic wave velocity. So we use slope of the curve, right? D sigma d epsilon, like let's say. So that um, will be, the slope of the curve will be higher if the strain hardening is higher. So then your velocity should increase, and that means I think, um, yeah, velocity will increase, and uh, that sometimes mean that, um, I think, that to extend to which, or I mean, the length of the plastically deformed part of the, this is Taylor experiment, right? You were talking about Taylor experiment. What I'm saying, that length of the plastically deformed part can be higher in this case. I mean, if the strain hardening is more, because your plastic wave velocity will increase, and then I think the elastic wave velocity will reflect back and hit the plastic wave. But if your strain hardening is more, then your plastic wave velocity is higher than a material with less strain hardening, then the plastic wave will travel more, and that means the plastically deformed part of the material will be uh, longer. The plastically deformed part of the material will be longer than that of a material with lower strain hardening. That's what I think, the answer to your question. And then somebody, prevent the release wave from entering the target material. Will the shock wave will continue forever, or will never dissipate? Ideally, yeah, it looks like the wave should never dissipate. Ideally, it should be the case, uh, but anyways, there will be interaction from the boundary. So we are not talking about an infinite body here. There will be interaction from the boundary. So if you are talking about a, let's say, wall kind of, you know, well, let's say we are talking about a wall, and then you are hitting from one side, and then um, even if you do not have a, let's say you are saying that release wave, then certainly the shock wave will be getting reflected from the other side. Or if it is a not a very wide sample, let's say you have I mean limited what is called, that is width of the sample, then again the reflection will happen from the other boundaries. So I think these interactions, as I told earlier also, the reflection from the boundaries will dissipate the shock wave. So that will surely interact. At least it will not like that whatever you ask, no, that will continue forever. I think it will not be like that if you do not have that kind of infinite domain. And the sign of the particle velocity was inverted because a positive stress causes a negative particle velocity upon reflection. The compressive wave upon reflection with tensile impedance of A is assumed higher, and the tensile reflected wave will move away from the interface. The tensile wave velocity and particle velocity are opposite to each other, so the reflected wave particle velocity should be towards the interface. Then how does the above statement is valid? So it should be like the positive stress causes a positive wave velocity or negative wave velocity if the impedance is lower reflection. Actually, yeah, there is a confusion here. I probably did not explain it properly. Um, I understand what you were saying, because I checked before coming here. I actually checked what video you were talking about. That is, I think, the reflection of like in a bar we have two parts. One has A and other part is B. One has higher impedance. I think the travel is going from A to B, and A has a higher impedance than B. So yes, there is a confusion here. I think whatever I told probably that is, I think, UP, if I am not wrong, UP equal to sigma rho c or something like that. That portion you were talking about. So it is, I think, because of the negative, I think, the sign convention, because it is the sigma r that is reflected stress is taken as I think negative. Then I think that this is minus sigma r, and that if you take sigma r as negative, then it will give you as positive. So that's the thing. Somewhere I probably didn't explain it well, and sorry about that. But that sigma r, the sign of the sigma r, I think is should be taken into consideration. That way you will get that particle velocity as positive. Yeah, whatever you wrote is correct. I mean, this is I think I have made some confusion I made here. So yeah, about the other question we have, that PDF I already told, and there are a lot of questions here from yeah, we do not have much time, so I will just quickly see. The specimen length is shorter than the wavelength of the elastic wave, so that the specimen is uniformly stressed. Why we want the specimen is uniformly stressed? Basically, in the Split-Hopkinson preserver, we want to have a what is that called? Uniaxial stress strain curve, right? So uniaxial stress strain curve. So at a particular strain, we draw a particular stress, right? So we do not want like variable stress values in the specimen. We need a uniform one. We want to draw a stress strain curve. So as you can understand, for the dynamic deformation, if you take a long rod or long specimen, so you have different stress value as at different point of uh, uh, different point of you know different cross section of the length, right? So that we don't want. We want to have a plotted stress strain curve where our material is like uniformly stressed at a particular strain value. We have a stress value and we can draw a stress strain curve. And then wavelength, yes, does the material properties, yes, that depends on the material properties. Wavelength depends on the material properties, and also same material for projectile incident. Yes, I think in most of the cases where I have seen, I do not have any speed of concern preserver here, but wherever I have seen or papers, I think they use the same bar, but I think some experiment they can vary it. See, it depends on what you want and how you want to calculate. Because if you know the physics, if you are really expert, then you can calculate everything. I mean anything, right? So whether it is basically, let's say you assume for a sample of aluminum alloy, they use a merging steel bar. Even for steel sample, they use a merging steel bar, which is high strength. Then, for if you want to get a softer material, let's say some polymer kind of, they can use even aluminum bar, or sometimes they use nylon bar. If it is a very high strength material, high strength or very high hardness material, then they can use even merging steel bar is not enough. They use tungsten carbide bars. So what I know is generally they keep the same striker. I mean, incident bar and transmitted, but that's what I have seen. But there may be some condition. I am not so aware of this point of time, and that you can use. Okay, let's say you have some difficulty in using the tungsten carbide projectile. Then probably you can try something else, but then that way you need to calculate, you know the things you need to calculate. There may be some changes because if you are using different bars. And then uh, yes, the elastic constant relation. Yeah, if you want to do a FEM simulation on that, probably yes, you can do elastic relations. But otherwise, we do not do. What we do, we just put the strain gauges and the incident bar and the transmitted bar, and then we get the readings, right? So, but if you want to do a finite element simulation or so, then yes, you will be using elastic properties. So I think, and amplitude repulse would imparts, and what strain rate limit when the wave initially enters the specimen reverberation. What does the reverberation mean? The inertia effects are not considered. Why do we take the incident bar and transmitted bar long? What parameters should be considered? There are a lot of questions here. So I will get back to these questions, and we do not have much time. And also there is another few questions. And how can we compare the strength of the material, the high strain to the high strain rate? Say strain rate of the order of strength of the material. Okay. So these things I will answer because we have maybe probably have 5 more minutes. Mm, so so what I want to tell you um, about the exam. So about the exam, I think you know that this is will be the same pattern as the assignment, and even you can get some of the questions from the assignment also. That is maybe very similar to assignment. That is because these kind of MOOCs courses, that is the rule. I mean, some of the questions are very similar to the assignment. So you will not get very different questions. That is everything will be same, I think. And uh, and as you know from the assignment, you will be I mean, NPTEL team will select only some of the assignments and your best assignments, and then we will see. So I think hopefully if you have seen, because I think this course is very less syllabus, what I feel, although there are not good reference book, or maybe some part I probably could not maybe explain you properly, but still I think this is should be a easy course for you because it has very less syllabus. You can just go through the slides, and if you go through the slides, directly, I mean, I think you can do well. It will not have a lot of numericals, as you can see from the entire the assignments. We have very less numerical problems also, problems. And then I think that's what I am giving a hint that you will get quite similar to your assignments. Yeah, that's all I think. That's all I think. I will upload this tonight. Hopefully most of the question, at least a few questions I need to check. Otherwise, I will upload it tonight. And I think, yeah, that's all. Any more questions, or otherwise we can leave? Yeah, I think, thank you. So I think all the best for your exams, and hopefully we'll all will do well in exam. Thank you.